So what we're going to talk about now is the next part of the internals discussion, and this will deal with how to process chunks in parallel. And that, of course, is what's going to involve the parallel stream. So we've already talked about how to split things up. Now we've got things into chunks, and now we're going to run those chunks in parallel. The way this works, of course, is by using the common fork join pool. And I'll kind of walk through the way that this works. It's really interesting to understand this. There's a great paper by my friend Doug Lee here that gives more detailed discussion of this, which I recommend you take a look at because it's very insightful. And here's basically what goes on. All parallel streams in a process, not in a pool, all parallel streams in a process are going to share the common fork join pool by default. So out of the box, you all use the same one. It's possible to change this, although it's very tricky. So what the heck is a fork join pool? Well, a fork join pool is basically an implementation of an executor service, which is a common way of being able to decouple the way in which threads are created and managed from the application code that is run concurrently. It's a very powerful feature that's been around since Java 5. And there's the thread pool mechanism that gives a way to do this executor service in a more optimized way. And so fork join pool is a class. And it provides some entry points to submit work to run from non-fork join task clients, as well as we'll see, once something is a fork join pool thing, there's other APIs for working with that. So here's the way that you as an external user can interface with the fork join pool. And of course, this is what the streams framework is doing under the hood on your behalf. So there's a couple of things. There's this thing called execute, where you give a fork join task and it will run it asynchronously. There's invoke, which will essentially block and return once it's done. And then there's something called submit, which submits the work for execution and returns a future to the work. So there's a couple different ways to process things. There's also a whole bunch of other methods that are used to manage and monitor the fork join pool. So for example, you can find out how many threads are part of the pool. You can figure out how many worker threads have been started but haven't gone away yet. So what's the current size? That could be dynamic. So get parallelism returns the target parallelism level, which is typically the number of cores on a machine, -1. Get pool size will return the number of threads that are created, which might vary dynamically. And then you can also get some other statistics, like how many threads have been stolen, or how many tasks have been stolen from a work queue. That just gives you a sense of how evenly split the work is. An end user typically doesn't muck around with these things at all. Well, that then begs the question, if we know what a fork join pool is, what's a fork join task? So a fork join task is essentially a chunk of data that you want to run in parallel, along with the functionality to apply to that data. That's what a fork join task is. And there are two primary methods defined in a fork join task. There's fork, which is used to asynchronously execute the task in the appropriate pool, and join. So fork join, right? So fork goes ahead and puts things in the right place, and then the thread pool will run them, and then join is called when the computation is done to get the result of the computation. And this whole thing is done in a very, very, very clever way under the hood. There's also a method called invoke, which is basically combining fork and join, and it just blocks. It waits for the result to be done, whereas fork does not wait. It's asynchronous. Now, it turns out that under the hood, a fork join task is a lightweight execution context. It's lighter weight than a Java thread. In particular, a fork join task does not have its own runtime stack, unlike a Java thread, which does have its own runtime stack. And as a consequence, the way that things work under the hood is you've got a whole bunch of threads, worker threads, that are the Java threads. Well, sorry, not a whole bunch. You have a relatively small number, typically about the size of the number of cores on the machine, plus or minus something. And then you've got the ability to have lots and lots and lots, hundreds or thousands or tens of thousands of fork join tasks. And because each of these things isn't a full-blown thread, you can have a whole lot of them. Of course, there are also some limitations with what you can do with them because they aren't a full-blown thread, but there's ways around that, as we'll see in a second. Under the hood, what's happening in the fork join pool is that there's this thing called a circular deck, where a deck is just an acronym for double-ended queue. And so that means that you can basically push items onto the top of the queue and pop items off the top of the queue. And you can also add items to the end, or enqueue items to the end of the queue, and dequeue items from the end of the queue. As we'll see, the most common operations are push and pop to the top and dequeue from the end. You typically don't end up adding stuff to the end. You typically just dequeue from the end. I'll talk about why that is in a second. So every thread in the thread pool that's managed by the fork join pool has a deck, and at any given point in time, that deck has work in it, which are basically the subtasks. In this case, if we're looking at parallel streams, these subtasks are the chunks that are created by the split iterator, by the parallel split iterator. It's splitting up the input source into chunks, and then it's putting those chunks into the appropriate decks of the appropriate threads in the fork join pool. Yes, Joe? We'll see. The question is, why is it circular? And an even more refined version of what you just asked is, why is it circular in the way it's circular? And the way it's circular, as we'll see here in a second, is it's super optimized, so it's possible to enqueue or dequeue from the front of the back in parallel without blocking. So as long as there's more than one element on the queue, on the deck, as long as there's more than one element on the deck, you can add and remove items from the deck without blocking things that are adding at the other side. Now, obviously, if two things try to add to the front, they'll be blocked, or one adds, one removes, that'll be blocked. But if you add at the front and remove from the back, those two threads can run in parallel. There's no contention. So that turns out, that's why. We'll see in a second. But let me first explain how it works. So whenever there's new work to be done, what happens is that the user of the fork join framework, which in our case is the parallel streams framework, is going to go ahead and push a new task or subtask to the head of its deck. So it's basically like pushing onto a stack, right? It's putting something on the head or the top. So if you think about what's happening with the parallel streams framework, after we've got ourselves atomic-sized chunks of work as a result of splitterating them, those atomic-sized chunks of work get stuck onto the head of some deck. It doesn't really matter, actually, which deck it is, and we'll see why in a second, but it gets stuck onto the front of a deck. Likewise, if a thread that's in the pool doesn't have anything else to do at the moment, and it needs more work, it goes to its deck, because every thread has its own deck. It goes to its deck, and it says, hey, is there anything for me to do? So in this case, using our example here, you can see that we had a subtask here that was pushed on, and now this thread needs to actually do work. So it turns around and it pulls or pops the item off the front of its deck or the top of its deck. Okay, so one interesting question is, why does it do that, right? That's kind of part of your question. Your question had a couple different parts, but one part is, why does it push and pop things onto the top of the deck? And the answer is because this enhances locality of reference and improves the performance of the cache. So if you've just pushed something onto your data structure, if you're a thread and you push something onto your data structure that you kind of manage, and then you turn around and pull it off again, it's probably still in your cache, right? Because it was just in your cache to begin with. You stick it into the deck. Now you take it back out. It's probably still there. So that enhances cache performance, and it also enhances what's called locality of reference. So that typically makes it faster, right? So there's less synchronization overhead and other overhead that comes from moving things around between caches. However, if for some reason our deck is empty, right? So you can see now our deck has become empty, and we're done processing, and there are other decks that have work to do, then a thread will come over and steal, that's the work stealing icon, it steals a subtask or a task from the tail of another deck, which is nominally managed by another thread, right? So it's work stealing, it's stealing the work. And the way it does that, and that comes back to your earlier question, it ends up taking that work from the tail of the other thread's deck. And the reason it does that is because that way we can have, that way the implementation can have it can basically have a lock for the head and a lock for the tail. And as long as this thread's pulling stuff off the tail and another thread is pushing or popping stuff on the head, those two threads do not contend for the same lock. So of course it's going to be much faster and lower overhead. Now again, obviously if we have multiple threads trying to add or remove things from the same part of the deck, then there will be contention, but that would be low. So that answers the question, why is it circular? It's circular so that we can have WorkStealing work efficiently when combined with the super cool synchronization mechanisms that are built into the deck, the circular deck that's used here. And so this is basically the place to go. Take a look at this paper, WorkStealing deck. That's what the implementation is based on, some variant of the algorithm described there. And it uses a circular deck to lower contention when used with WorkStealing. So super duper cool stuff, right? Not probably the kind of thing that mortals like us would likely want to write. We would much rather leverage somebody else's work to think this through so we could just make our code run faster. So one way to think about parallel streams, now that we've gone through all this discussion about how the fork join pool works internally, a parallel stream is basically just a user-friendly facade to all of this low-level fork join pool machinery, right? So they got this really super complicated, super cool, super optimized fork join pool thing, but hopefully, as you'll discover for assignment number 4, not that much fun to program, right? But super cool. The parallel stream just basically shields you from all that low-level gobbledygook. So you're just kind of writing functional programming logic, stitching it together with the streams, with lambdas and method references and stuff, and it's managing all the stuff underneath the hood. And the way it's doing that, of course, is by using the parallel splitterator to break up the input into chunks. Those chunks are then enqueued onto the fork join pool, and then, as we just described, the fork join pool will steal the work, the chunks that are on there, and then partition them relatively evenly across all the cores on the machine without you having to be aware of how that's working. And that's, of course, where the non-determinism comes from. You don't really know or care where they're running as long as they run, and they work fast. Now, for those of you who like pain, right? Anybody here seen Lord of the Rings? First Lord of the Rings? So remember, Saruman says to Gandalf the Grey, I gave you the chance to come willingly or join with me, but you have chosen the way of pain, right? There's a classic scene where they're battling it out in Orthanc, and that's his great quote. Well, that's what, if you're Gandalf the Grey, you might choose to program directly to fork join pool, right? Because you're a wizard, you're a super being. So you can do that. So here's an example that actually comes from a test case that I wrote just to prove that I could do it, painful as it is. And this uses the fork join pool directly in order to write code that doesn't use the streams. Not recommended, but it's cool. And so you can write like that if you want. And there actually are some other use cases where the Java 8 parallel streams programming model isn't really quite the right fit. So if you recall, one of the characteristics of parallel streams, you've really got to have input that splits evenly and efficiently. And if you don't have input that splits evenly and efficiently, parallel streams isn't really for you. But that isn't to say that parallelism isn't for you. It's just that the parallel streams model may not be for you. So there's certain things, where trying to use streams would be like trying to pound a square peg into a round hole, right? I mean, you can do it, but it's painful and makes a mess. So there's an interesting article here that shows how to use the fork join pool framework in order to do recursive traversal of a directory structure, which, by the way, is not unlike traversing the images in a nested hierarchy of HTML folders, right? That's a similar kind of thing, right? This happens to be searching in a directory structure as opposed to a website, but basically the same idea. And this illustrates how you can write code like that. So what we'll probably do for assignment 4, depending on how it all works out, the last assignment may be to redo your web crawler, except this time we'll use parallel streams directly. Oh, sorry, we'll use fork join pool directly. So you'll get a chance to play around with stuff like that. So, again, not the world's worst thing to do, but not as clean as writing parallel streams. Okay, so that's the overview of the first part of this discussion.